So number 3 says, find the nth order Taylor polynomial for the function centered at the given value of a. And for this one, we have f of x is equal to cosine of x squared. And we have n, meaning the order for the Taylor polynomial is 2, and the center value for a is 0. So just a reminder, when the center value is 0, we call that the Maclaurin series, just in case that vocabulary comes up for some reason. So that means we are supposed to find the second order Taylor polynomial for the function cosine x squared centered at 0. So,
you know what chapter this is? You know what section?
It is. In fact, I'm going to give you a page number to reference even better. So we introduced Taylor polynomials in 9.1. And since we're only on problem 3 in the overall chapter review set, it's usually from the earlier part in the chapter. This is a 9.1 problem. But specifically, there it is. So they said our goal is to find second order Taylor polynomial. So the Taylor polynomial, the definition for Taylor polynomials and the formula for how to find them is on page 664 in 9.1. And so the thing to get comfortable with or remember about a Taylor polynomial is that it's a polynomial where you have a constant term, an x term, an x squared term, an x cubed term, like that, where the degree is the order. And each of those terms has a coefficient in front of it. Excuse me. And the coefficient is given by the formula that you use to figure it out. So the coefficient for the kth term in the polynomial is the function's kth derivative evaluated at the center divided by k factorial. So in order to produce a Taylor polynomial, you're basically going to need the first, second, third, fourth, or however many you need derivatives of the function evaluated at the point in the center in order to come up with the coefficients of the polynomial and take those derivative values dividing by factorials as you go down in the polynomial. That's the formula. That's from that definition on page 664. And we just apply that. So first of all, when k is equal to 0, that means the 0th derivative, meaning I didn't take the derivative. Then I have f of x, the 0th derivative, is the function, cosine of x squared. And when k is equal to 1, then I need the first derivative. So I'm taking the derivative of cosine of x squared. I'd use the chain rule. The derivative of cosine is minus sine, and the derivative of x squared is 2x. So the 2x would pop out, and I would get minus 2x. That did not work. Sine of x squared. So there's the first derivative. So then to get the second derivative, when k is equal to 2, and again, I'm using these derivatives because the derivatives are in the formula for the coefficients for the Taylor polynomial. And using the derivatives is how you make the polynomial make a good proximate values for the function. All right, so then to use the second derivative, I need to take derivative of the first part, which was a product. So now I'm going to need to use the product rule. So to use the product rule, I'm going to sort of think of this as the left function and this as the right function. So the derivative of the left function is minus 2, which is times the right function. Then I add to that the derivative of the right function times the left function. So the derivative of, let's do that here. I drew. So the derivative of the right function times the left, I'm just going to put the left function and then write the derivative of the right function, which would be the result again of the chain rule. So the 2x would pop out and I would have the derivative of sine is cosine x squared. A little bit of simplification can go on there, so let's go ahead and do that. Maybe we'll just take a minus 2 out of the whole darn thing. And then I would get sine of x squared minus 2x cosine x squared. Actually, I have 2 x's there. 2x here, 2x here. So this x needs to be squared as well. Now, each of these derivatives need to be evaluated at the center point. And the center point is when x is equal to 0. So using this center point and trying to see what these would give me at a equals 0. So for cosine of x squared, when x is a 0, this is at a equals 0, that would be cosine of 0, which is 1. Doesn't want to work. Okay. So then in the next part, well, when x is 0, I think we have a factor of 0 here, so I think I would get 0. And in the next part over here, sine of 0 is 0, and I have a 0 here. This all seems to give me 0 too. That seems a bit surprising. So the polynomial, the Taylor polynomial of order 2 would be basically, let me write out the formal format so that you can see where this is going. We would have c sub 0 plus c sub 1 x minus 0 to the 1 plus c sub 2 x minus, I should say a here, and then fill in all the details squared. So this is the basic formula from the definition that in each case you have the coefficient of the 0th, 1st, 2nd, 3rd multiplied by x minus the center value raised to the 0, 1st, 2nd, 3rd, etc. So if we're going up to 2, we would stop at 2. A is a 0, and our 3 coefficients would be found using the formula up here, where you take the derivative evaluated, in our case at 0, dividing by k factorial. So in the first case, we got that the function evaluated at 0 was 1 divided by 0 factorial times x minus 0 to the 0. You don't have to write all this in, but I'm just trying to help illustrate how the formula is at play here. So then when k is a 1, we got 0 as our first derivative over 1 factorial times x minus 0 to the 1. And when k was a 2, we still got a 0 for the derivative, which is why I checked it, over 2 factorial times x minus 0 to the 2nd. And if we simplify all this, this term is a 0, and this term is a 0, and this term is a 1. So our second order Taylor polynomial is just the constant 1. So looks kind of silly, but they just have a kind of silly example here. It's because the next two terms all dropped out. But I did check it in the back just to make sure it wasn't a silly mistake on my part. And yes, that's what they wrote as the answer. Questions, comments, discussions about this? See if I can get all this on the page at once. There we go. About this number 3 problem from the Chapter 9 review exercises, in which we created a second order Taylor polynomial using the definition on page 664. Questions at all? So you said, isn't 1 divided by 0 undefined? That's a great question. We didn't divide by 0, we divided by 0 factorial, which, yes, the definition of 0 factorial is 1, as Wenzel is pointing out. Dima is asking, how do you use these derivatives to write the polynomial? Oh, and somebody said there should be a plus in there somewhere. If I had supposed to have a plus in there somewhere, I think it would have zeroed out anyway, but let's see. The plus 2x squared cosine x squared plus 2x squared cosine x squared. So let me just double check that. So Paimon, I think, are you talking about right here? This part here, that you think that should be plus, a plus inserted in there or something? Or maybe you mean down here, because I factored out the minus? Yeah, that must mean what you're talking about. Yeah, I think you're right. I factored out the -2 and then I didn't, so that should be a plus. So yeah, he's right. So let's just to focus in, devil's in the details. I like that one. So yes, this should be a plus here. That's what he's saying, because we factored out the minus out front. Absolutely right. The whole thing got zeroed out, so it didn't affect the answer, but you're absolutely right. That should have been a plus. Thank you for the correction. So in 13, it asks us to find Taylor polynomials of order 0, 1, or 2, and 2 for the given function centered at a given point, and then make a table showing the approximations and the absolute error in these approximations using a calculator for the exact function value. Okay, so this is a technology problem because we're going to use calculator for our table, but I think I'm just going to do the second derivative part because the 0 and first orders can be seen from the second order Taylor polynomial. So if I interpret the problem that way, then let's see which function we are given. The function is just sine x. We are given a value of pi over 4. Oh, that's good. It's not 0, something a little bit more different. Interesting. And we're supposed to approximate sine of pi over 5. Okay, so we're going to find the second order Taylor polynomial and the absolute error of that approximation. Questions about the statement of the problem?
Is this still 9.1?
Yeah, so anytime they ask us to find a particular order Taylor polynomial, that was all in 9.1. In 9.2, we went on to general power series, and then we looked in 9.3 at Taylor series, where we then didn't just do an nth order, but we let n go to infinity. So as long as they're a finite order Taylor polynomial, that's still in 9.1.
Okay.
So we would be using the same definition, except now we have a new term written in here where you may or may not recognize the absolute error. And so the absolute error is just the absolute value of the difference between what the function's real value is, which we're supposed to use a calculator to figure out, and what the polynomial would approximate it to be. All right, so let's do what we did before. So we're going to consider, to get a second order, we're going to consider when k is 0, when k is 1, and when k is 2. When k is 0, we're not taking any derivative. Then we just have the function, which is sine x. When k is 1, that means we want the first derivative. Derivative of sine is cosine. And when k is 2, that means we want the second derivative. So we take the derivative of again and get minus sine. And again, the coefficients involve the formula of the derivative evaluated at the center. And so now we want to look at this at the center value of x is equal to pi over 4. So sine of pi over 4 is square root of 2 over 2. Somebody will correct me if my trig memory is wrong. So cosine of pi over 4, which is the first derivative value, is also square root of 2 over 2. And minus sine would be negative square root of 2 over 2. So then I might as well extend that and then say then we can try to figure out what is c sub k for these k values. And again, c sub k is where you take that derivative, that kth derivative at a, and just divide it by k factorial. So in the case of dividing by the 0 factorial, which is 1 instead of 0, we would just get square root of 2 over 2. In case where k is 1, we're dividing by 1 factorial, so we still get square root of 2 over 2. However, in the case of k is 2, we're dividing by 2 factorial, which is 2. So then we'd get minus square root of 2 over 4. So just to point out, we divide by 0 factorial, we divide by 1 factorial, we divide by 2 factorial to get c sub k. Questions at all about my process or how I'm coming up with the second order Taylor polynomial for sine x at a equals pi over 4? Okie dokie. So now let's see if we could write out the polynomial. So we want to write out second order Taylor polynomial. So the first coefficient is the square root of 2 over 2. Then the second coefficient is the square root of 2 over 2. And we're going to multiply that by x minus the a value, which is pi over 4, raised to the first power. So I'll just leave that like that. And then the second degree term would be the coefficient. Actually, let's take one of those back, which is minus the square root of 2 over 4 times x minus the a value, pi over 4, but now it's raised to the second power. So the first part of the problem where they wanted us to create the 0, first, and second order Taylor polys, well, the 0 one would be the number in front. The first order would be the first 2 terms up to first degree, and the second order would be all 3, which you have here. So those are you can kind of see by looking at the second order Taylor polynomial what the 0 and first order ones would be as well, by looking at the first couple of terms. So that was the first part of the problem. Questions, comments, discussions about how we came up with this? Okay. So next we want to find the absolute error when x is equal to pi over 5. So what does that mean? That means the absolute of the error, where the error is the difference between the function's value and this approximation. So this would be the absolute value of sine of pi over 5. That's what the function gives us, minus what the approximating polynomial gives us, p of pi over 5. So that's the absolute error. So let's not bother to do that. That's a calculator problem at this point. I would literally type sine of pi over 5 in the calculator, and I would type pi over 5 plugged in for x into the polynomial above here, and then I would take the difference, and I would round off somewhere. What does it say? Does it say we're round off? No, it does not. But if it was in my math lab, they would. And then this would give you the absolute error. So in this one, it says, use the ratio or root test to determine the radius of convergence of the following power series. Test the endpoints to determine the interval of convergence when appropriate. And for number 17, they give us the following power series. And they have, well, they don't even bother to write the limit, so but it's k squared x to the k over k factorial. So what are we supposed to do? Find R, radius of convergence, and interval of convergence. I'm still learning how to do all this stuff, so I'm experimenting a little bit. Thanks for participating. Okay, so again, what is the goal? What is the big picture issue? The thing to recognize is that this is a power series. So you can think of it as a polynomial. It's an infinite degree polynomial. And depending on when you plug in something for R, it may converge or it may diverge. So big R is the radius of convergence. And the interval of convergence will literally be an interval of values over which the power series converges. And so we are often tasked, and this began in 9.2, so this is definitely sort of a 9.2 problem at this point, to find the radius of convergence and the interval of convergence. And the number one method to do that is usually the ratio test. So the idea is to use the ratio test here. We would let R be equal to the limit as k goes to infinity of the absolute value of a sub k plus 1 over a sub k. This is what we looked at in chapter 8 when we did the ratio test. The difference in chapter 8 is that the a sub k or k plus 1 terms didn't have a variable in them. They just had some formula for some k values. Whereas now we also have a variable included in the term. And the idea of the ratio test is that if the result you get when you take this limit is less than 1, then you get convergence for that series. So what we're going to do is do this with a variable in there, and then that'll give us an inequality in x that we can solve for x to see which values would make this limit less than 1, and therefore which values of x would cause this power series to converge, which is the goal. There'll be a radius of convergence and an interval of convergence we can get from that. So applying this formula, again, we plug in k plus 1 everywhere there's a k. So that means R is going to equal the limit as k tends to infinity of k you can do it. K plus 1 squared instead of k squared, x to the k plus 1 power instead of the k power, and k plus 1 factorial instead of k factorial. So that's a sub k plus 1. Then we would divide that by a sub k, which is the formula we're given in the first place. So since a sub k and a sub k plus 1 are both fractions, when I divide by a sub k, it's easier to multiply by the reciprocal. So I would take the original formula for the function and turn it upside down, giving me k factorial in the top and k squared and x to the k in the bottom. And again, we're taking the absolute value of all of this, and we need this to be less than 1 in order for the series to converge. Questions about the setup for the ratio test for this problem? Okay, looks like I am not falling behind on chat questions yet so far on this problem. Okay, so we reorganize and we cancel a little bit. So let's see here. I'm going to say that this is equal to the limit, if screenwriting will allow me to. The limit as k goes to infinity. So I'm going to put the squared things together, and that's going to give me k plus 1 over k squared. And I'm going to put the factorial things in the same fraction. So that's going to give me k factorial in the top and k plus 1 factorial in the bottom. And then I'm going to put the x together in their own fraction, which is going to give me x to the k plus 1 in the top and x to the k in the bottom. And so now if you remember from doing ratio test in chapter 8, here's where we get to do some simplification. So for example, k plus 1 factorial is k plus 1 times k factorial. Since you multiply by the numbers counting down, we can pull off the biggest number, k plus 1, and then after that multiply by k factorial. And that's helpful because then these cancel out. Similarly, if I have x to the k plus 1 in the top and x to the k in the bottom, when I divide, I subtract the bottom power from the top exponent. K plus 1 minus k would just leave 1. So that means that with this one, the k, x to the k on the bottom cancels out everything except a single x in the top. And we also may remember that a limit of a product is the product of the limits. And I can take the limit as k goes to infinity of this leftmost fraction, k plus 1 over k squared. And I can take the limit of the inside part, and I'm going to just get 1. So at this point, I have the limit as k goes to infinity of the absolute value of x over k plus 1. And I need this to be less than 1. And all the values of x that will cause that to be less than 1 will be values for which the series converges. Questions or comments up to this point? Okay, well, the thing to notice here, it converges regardless of x. So yes, Wenzel's exactly correct. The thing to notice here is that the absolute value of x will just be some number we plug in that stays fixed while k is busy rushing off toward infinity. I can plug in a 7 for x, and then I get 7 over k plus 1. And since k is going to grow huge while the 7 just sits there, that's going to be less than 1. That's going to go to 0. Then in general, this entire thing, no matter what I plug in for x, goes to 0. That's always less than 1. So that means x can be any number. And so since x can be any number, going back to our original goal, that means the radius of convergence is infinity, and the interval of convergence is anything from negative infinity to positive infinity, all real numbers. So it says, use the geometric series to determine the Maclaurin series and the interval of convergence for the following functions. And for 26, we have f of x is equal to 1 over 1 plus x cubed. So ultimately, the goal is to determine the Maclaurin series and interval of convergence. So find the Maclaurin series, which is just the Taylor series at 0. And the interval of convergence. But in particular, it says to do this using the geometric series. Question is, how do we use the geometric series? So I think the idea about using the geometric series is that we know that power series for a function as a given, so that we start with that, as opposed to, for example, going back to the definition of a Taylor series where we would have to use the formula and take derivatives and stuff. So I think that's what they mean by use it. So let me write up what the Taylor series is as a reminder, because they actually gave that in the problem. I'm sorry, what the geometric series is. So remember that the geometric series, and again, as a reminder, this is one of the things that we're going to refer you to the table 9.5 on page 694. On page 694, at the end of 9.3 is table 9.5, where they have basically all of the results from all the series that we did. And one of them is the geometric series is the first result because it's kind of simplest. So from that, we have that 1 over 1 minus x. And this is the one we started with because it's also the simplest power series. 1 plus x squared plus x cubed, etc. And that this is valid as long as the absolute value of x is less than 1. Because again, this is the geometric series. Each term you're multiplying by the same number every time. So we're multiplying by x every time. So as long as that multiplier every time, that constant ratio is less than 1 in absolute value, then this converges. This is a geometric series that converges, and this is the formula for what you would get. So definitely look at this table a lot. Try to become familiar with what's on it and how to use it and stuff like that. So in this problem, they're telling us to use this as a given to find the series for 1 over 1 plus x cubed. So the way we would do that is we would basically say, I want to somehow replace x in the power series for a geometric series in a way that I'll end up with this function up here, and I'll have a new series for that new function. So I'm going to write 1 over 1 minus, and I need to be able to put something in for x here. And if I did that, I would mean I'd also be putting something in for x on the right as well. And that would be good whenever that's something I put in there, an absolute value less than 1. So these Taylor series are functions. You plug things in, you see what you get. And we had a theorem that said when we're using series, you can get new series by adding other series or by multiplying by some power function or by substituting some power function, which is what I've left open for now, because that's what we're going to do in this case. So the question is, what can I replace x with? So I'll end up with 1 plus x cubed. So since I have a minus, that means I want to have a minus in here to make it a plus. And instead of x, I want to have x cubed. So that means if I put in minus x cubed there, it will simplify to the function that's my goal. But I need to have x minus x cubed here, and minus x cubed here, and minus x cubed here, and minus x cubed here. So in this way, I'm using the known geometric series, and I'm substituting into that to come up with a new series for the power function that they asked for. The power series for the function that they asked for. So that would mean that 1 over 1 plus x cubed is 1 minus x cubed plus x to the 6th minus x to the 9th, etc. And this is going to be good when the absolute value of x cubed is less than 1, but that's the same as when the absolute value of, without the minus of x cubed is less than 1, which means the absolute value of x is less than the cube root of 1. So the absolute value of x still just has to be less than 1. So I can write a formula for this, but this is basically the idea that I used the geometric series to come up with a power series for this new function because they were similar enough that I could get the power series for the new function by substituting in to the geometric series. Questions, comments, discussions about this problem? So you could try to do this using the formula for the Taylor series with the derivatives and all that stuff. But just this is drastically easier, and they really wanted you to do it this way. That's why they gave the instructions the way they did. Okay, so let's do, can we have more of these problems? Yeah, let's do one where there's a little bit more interesting stuff going on. I'm going to do one more, and then we'll take a break so that we have time for 10.1. But this will be a good one to finish on, I think. At least I think so, but you guys can disagree. So consider, what if the goal is to find a power series for the integral of sine of x squared dx. So I'm putting this up as an example because when we were busy in chapter 7 learning how to integrate, and how to use tables of integrals, integration by substitution, integration by parts, one of the things that I discussed with the class at the time is that there are some integrands, some things where there is no algebraic antiderivative. And this was one of those examples, e to the x squared, sine x squared. You can try to do this by substitution, parts, whatever you use, it's just not going to work. There is no algebraic antiderivative for this. So what that puts us in a position is in the same way that sine of x itself is a transcendental function, not an algebraic function. Well, the antiderivative of this is not an algebraic function, but what we can do is instead consider it as a series. And if you have a power series, you can integrate term by term. So the clue here is that they're not asking us for an algebraic expression for this, they're asking for a power series for this. So the idea would be is that first we could say, can I come up with a power series for sine x squared? And then if so, I will just integrate that term by term in order to get the integral of sine x squared as a power series. So again, going back to the table, (9.5), we know that sine of x is equal to odd powers over their factorials alternating, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. And this is for all x. Radius of convergence is infinite. So, like we sort of did in the last example with the using the geometric series, we can use this series to then realize that therefore sine of x squared can be written as a power series where I replace all the x's with x squareds. So that would be x squared minus, and if I square it but then cube it, I get x to the 6th, but still over 3 factorial. And similarly here I'd get x to the 10th over 5 factorial. So now I have a power series for sine of x squared. So if I want a power series for the integral of that, I would integrate both sides. So then I get that the integral of sine x squared dx is x cubed over 3 minus x to the 7th. So if I integrate that, then that's over 7, but it's still times 3 factorial plus x to the 11th power over 11, but still over 5 factorial, etc. So that's the first few terms of the power series at least, but to do it right, to really know the power series, I should really write it as a formula. So I'm going to rewrite this as a summation. And let's say we let k go from 1, why not, 1 to infinity. So we have to come up with a formula for this, where we have the powers that come out, right? So we can see, for example, that the powers keep going up by 4 each time. 3 goes to 7, goes to 11. So we're adding 4 each time. So they're somehow similar to a multiple of 4. But in this case, when k is a 1, instead of at 4, it's at 3. When k is a 2, instead of at 8, it's at 7. So we're multiplying k by 4, but then subtracting 1. So this means I would have x to the 4k minus 1. So then as k is 1, 2, 3, 4, 5, etc., that's the power that I would get. Then whatever that power is, I'm dividing by that power because we integrated. So then I would divide by, try that again, divide by 4k minus 1. And then I'm supposed to multiply that by this number down here, which was somehow related to the power. Basically, we got these numbers here because they were half of what the power was before we added 1. So if we added 1 to get back to this, I would have to subtract 1 from that again to get back to 10 and then divide by 2. So instead of 4k minus 1, I need to subtract 1 from that, and I would get 4k minus 2, but then I would divide that by 2. So for example, when I'm at 3, 4k would be 12. 12 minus 2 would be 10, divided by 2 would give me 5. When I was at 7, 4 times k being 2 would give me 8, minus 1 would give me 7, but if I minus 1 again, I get 6, and then divide by 2, I get 3. So if I divide by 2, this just becomes k minus 1. I'm sorry, 2k minus 1. So I'm going to simplify that. So this becomes 2k minus, let's try that, right, k minus 1 factorial. And we can double check that we believe our notation is right. So when k is a 1, this would be 1 factorial. 2 minus 1. When k is a 2, we get 4 minus 1 factorial, which is 3 factorial. When k is a 3, we would get 6 minus 1, which is 5 factorial, etc. So this would be our answer. This is the power series for the integral of sine squared x dx. And that can be used to evaluate this. It has an infinite radius of convergence. Or you could, go out the first few terms to get a polynomial that approximates this as good as you would like.